Howdy, howdy, this is Mr. Potter. In our last video, we talked about how to break apart a number into components, powers of 2, that add up to the number. And we noticed that we ended up with a unique way to build a number based on those powers of 2. What I want to do today is I want to talk about how computers use that information to store data, as well as how humans use that information to interpret the data that computers have to offer. So I actually want to start by talking about what we did last time. So let's say that I have some number, let's say, 91. And what I want to do is I want to take this number and I want to break it apart into the components of the powers of 2. So I'm just going to list my powers of 2 up here. I've got 2, I've got 4, I've got 8, I've got 16, I've got 32, and I've got 64. The next power of 2 is 128, but I'm really not going to need that because 91's too small. And of course, don't forget, 1 is also a power of 2 because that's really 2 to the 0. So I know I'm going to need a 64. So I could write this as 91 is equal to 64 plus, and of course if I take 91 and subtract 64, that's going to leave me with 27. So now I've got the 64 has been used. The 32 is not going to be used because 32 is too big, but the 16 will. So this is 64 plus 16, and if I was to take 27 and subtract 16, that's going to leave me with 11. So I'm probably going to need an 8, and I know that 11 minus 8 is a 3, so I'm not going to need this 4, but I could use the 2 and the 1. And so what I've now here is I've got this binary decomposition of 91 written in terms of powers of 2. So this is what we talked about last time, how we could take any number and break it up into powers of 2. And this is a unique representation. There's no way I can do it without getting the 64 because all of these numbers that we've got are not big enough to get up to 91. We learned last time that all of these numbers are all going to add up to 1 less than this power of 2 that I've got here. So what I want to do now is I actually want to take a trip back to first grade. So back in first grade, when we saw a number like 91, we talked about something called place value. We talked about how this was our tens place and how this was our ones place. And so I could take a look at any number and talk about how many ones it had, how many tens it had, how many hundreds, how many thousands. Each one of these digits represented some place in this value of the digit. And then when we got to our algebra class, we would talk about, oh, the tens place is really 10 to the first power. And the hundreds place, of which I have none, is really 10 squared. And this ones place, this is really a fancy way of writing 10 to the 0 power. So we could talk about the place value not only in terms of what we learned back in first grade with a hundreds place, a tens place, and a ones place, but we could also talk about it in powers of 10. So 10 squared, 10 to the first, and 10 to the 0. And of course, the reason I bring that up is because remember, 91 is equal to 64 plus 16 plus 8 plus 2 plus 1. So what I've really got here, this is really 2 to the 6th power. This is really 2 to the 4th power. This is 2 to the 3rd power. This is 2 to the 1st power. And this is 2 to the 0th power. So I could think of 91 as being digits in some system, where I've got my 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, and I need one more spot for 2 to the 6th. So I could talk about whether or not it's present. 2 to the 0 is present, 2 to the 1st is present, 2 to the 3rd is present, but notice that we skipped this spot. There's nothing there. And then I've got 2 to the 4th, which was present, and 2 to the 6th, which is present, but 2 to the 5th, again, nothing's there. And so what happens is I've got this 91 written as what we call a binary number. 1, 0, 1, 1, 0, 1, 1. And we'll often see a 2 written down here to show that this number is in base 2. We don't usually write a 10 for the subscript when we're dealing with a number like 91. We don't usually say 91 base 10 unless it's ambiguous because we have different numbering systems. What you really need to recognize here is that these numbers are either going to be present or absent. And if they're present, I used a 1 to indicate that they were there, and if they're absent, I had a 0 to indicate they were there. So what I've got here is I've got a decimal number, but I've converted it to a binary number. This decimal number is in base 10 because all of my powers are powers of 10. This binary number is all in terms of powers of 2. So what we're going to be doing quite a bit of in this first unit is converting back and forth between these different values. In other words, if I have 110010 in base 2, the question is, how do I convert that to something in base 10? So I'm looking at this. This is supposed to be my 1's place, my 2's place, my 4's place, my 8's place, my 16's place, and my 32's place. And so my answer is really going to be 32 plus 16 plus, there are no 8's, there are no 4's, there is a 2, and there is no 1. And so I've got 32 plus 16, which is 48. 48 plus 2 is 50. And we say this is 50 because there are really 5 10's and 0 1's, or 0 units. That's our base 10 representation. If I was, in fact, to start with 50 in base 10, I could list all my powers of 2, but there is another way to deal with this. I could take 50 and divide by 2. Now 2 goes into 50 25 times, and we're doing this old 3rd grade division, which means I'm using R for remainder. Now notice my remainder is 0, which means I have no leftover 1's. So I have 0 1's. And that means this 1's place has to be a 0. Now I'm going to take this 25. Now remember, this is really 25 2's that are in 50. If I divide by 2 again, that's going to tell me how many 4's there are. So I'm going to have 12 4's in 50. But with a remainder of 1, because 2 goes into 25 12 times with a remainder of 1. And this means I have 1 2 hiding in that value. So my 2's place digit will be a 1. And I continue to divide these numbers by 2 to figure out how many of the next set there are. 2 goes into 12 6 times. And really that means that there are 6 8's in 50, because 6 times 8 is 48. And I had this 1 2 that was left over. My remainder when I divide 12 by 2 is 0, so I have 0 4's. So I have 0 4's. Now if I were to take 6 and divide by 2, 2 goes into 6 3 times with no remainder. And so because my remainder is 0, that means I have 0 8's left over. I could think of this as 3 16's with 2 left over, because 3 times 16 is 48, and 2 more makes 50. If I try this again, if I try and divide by 2 again, 2 goes into 3 one time with a remainder of 1, which means I have 1 16. And of course, I had no 4's, I had no 8's, I had a 16. And now if I take this 1 and divide by 2, I end up with 0 with a remainder of 1, which means I've got 1 32. And so doing this sequence of division, repeatedly dividing by 2, and then writing down the remainders from right to left. That's how I'm getting the digits in this binary representation. Remember that this is the base 2 representation of 50. And so what this does, this allows me to transfer from the way that a computer would look at storing a number as a series of bits, as a series of 1's and 0's, ons and offs in memory. And I can go back and forth between writing a binary number as a decimal number, or writing a decimal number as a binary number. Now the reason that humans don't use this that often is because these binary numbers are very long. Keep in mind, last time when we were talking about a number like 255, this only takes 3 digits in base 10, but it actually takes 8 digits in binary. And so writing numbers in binary takes a lot of space, takes a lot of time. Now computers go through these very fast. If I'm talking about a machine that's a 3 gigahertz processor, that means it's doing 3 billions of these bits every second. So the computer can deal with this very fast. Humans, on the other hand, we're a little bit more mundane. We can't handle it that fast. And so what we do, rather than grouping in this power of 2, we group in a different power of 2. The idea of octal numbers. Octal meaning base 8. Now, if I were to look at a number that was written in base 8, of course, I'm still going to have my ones place, but the next power would really be 8 to the first, or my eights place. And the next digit would be the 8 to the second, or my 64s place. And so this is another way that I have to represent a number. Now, what's important is if I go back and I think about my binary numbers, my binaries would either be the digit 0 or 1, either an on or an off, because my remainder could never get up to 2. It would always have to be the whole numbers up to, but not including, my dividend, or my divisor, I should say. So if I look at it here in base 8, the possible digits are going to be 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7. In other words, all of the numbers up to, but not including 8. So in these spots, I'm going to have digits 0 through 7. But the process is exactly the same. If I wanted to convert 91 in base 10 to some number in base 8, I'm going to repeatedly divide 91 by 8. Let's see, 8 goes into 9 one time, leaving a 1. 8 goes into 11 one time with a remainder of 3. So I have 11 eights with 3 left over, 3 ones left over. So now I'm going to take this 11 and I'm going to divide it by 8. So 8 goes into 11 one time with 3 left over. So this means I have 164 with 3 eighths left over. If I continue to divide by 8, I'm going to get 0, because 8 goes into 1 0 times with the remainder 1, and I end up with a 1. So I end up with 133 in base 8. And so I have an easier way to represent this. Now this is still a power of 2. One thing to keep in mind is that if I wanted to convert this to base 2, the process is pretty straightforward. I need to convert a 3 into base 2. But remember that because 8 is 2/3, each one of these digits here is going to go down to 3 digits in my base 2 representation. This second 3 is going to deal with 3 digits in my base 2 representation. And this 1 is also going to be 3 digits in my base 2 representation. So I've got this 3 here. Now 3, if I wanted to write that in base 2, I know that I need a 2 and a 1, but no 4s. And similarly, this 3 is going to be exactly the same. No 4s, a 2, and a 1. And if I wanted to write 1 in base 2, I'm going to have no 4s, no 2s, and 1 1s. So I could say that this is 1 0 1 1 0 1 1 in base 2, and just kind of not write these leading zeros, just like I don't write the 0 in the hundreds place when I wrote 91, or I don't write the 0 that's in this 512's place in my base 8 representation. So we could do another example of this. I could take the 50 that we were dealing with earlier and divide it by 8. 8 goes into 50 6 times, because 6 times 8 is 48, with a remainder of 2, which means in my base 8 representation, I have 2 1s left over. And if I divide 6 by 8, I have 0 with a remainder of 6. And so I end up with 62 base 8, which is what 50 in base 10 happens to be equal to. And similarly, I can break this up into a binary representation. So this would be 0, 1, 0. That's what 2 looks like. And 6 is 4 plus 2 plus no 1s. So 50 in base 10 could be thought of as 110010 base 2. It's very convenient. It's even got the commas at every group of 3 numbers like we expect when we're writing really large numbers. But I think that this 62 base 8 and this 133 base 8 that we have are much more succinct ways to do this. But we also have the ability to go back and forth between the binary representation and the octal representation very quickly. If I was to write one more number over here, let me write one number like, I don't know, how about 110101101? I just made that up. But if I group this into 3s, so this 101, that's a 4, no 2s, and a 1. That's a 5 in base 8. If I look at this next set, oh, there's another 101. That's another 5. And then I've got this 110. That's a 6, because 4 plus 2 plus nothing. And so now I can look at this. I know this is my 1 spot, this is my 8 spot, and this is my 64's spot. So if I look at 64 times 6, well, let's see. 6 times 4 is 24. Carry the 2. 6 times 6 is 36. 2 more makes 38. And then I've got 5 8s, which is another 40. And I've got 5 1s, which is 5. So if I total this up, I've got 429. And so this is my base 10 representation of this base 8 representation of this base 2 representation. Now, for humans, because we have 10 fingers and 10 toes, this is the preferred way. For computers, because all it's doing is turning on and off a light switch, this is the preferred way. And this, because it is a power of 2, but the digits are very close to our 10-digit system, this is kind of a nice compromise, this octal number system. And a lot of computers store numbers in octal for human readability. They also store numbers in another power of 2 because 8's a little short for 10. And 16's a little big, but it's another way to look at this. Now when I say hexadecimal, this is really 6 plus 10, so we say this is base 16. And there is a problem with base 16. One of the problems is, of course, a 0 is a 0, and a 1 is a 1, and a 2 is a 2, and a kept going, I'd say an 8 is an 8, and a 9 is a 9. But if I get a 10, there has to be one digit that represents 10ness. And the question is, what digit represents 10 in our hexadecimal system? What digit represents 11 in our base 10 system? Or 12, or 13, or 14, or 15? Because remember that the largest number that I could ever get would be a remainder when I divide by 16. So it could be any value from 0 to 15. And as mathematicians, we are lazy. So we say this is an A. We say this is a B. We say that this is a C, and a D, and an E, and an F. So when I start looking at hexadecimal numbers, this is where I start seeing A's, B's, C's, D's, E's, and F's. And when I see representations in memory, I'm going to see these a lot. Most times when I'm dealing with computers, I'll see these hexadecimal numbers. And you may also remember that we talked about bytes in our last lecture. Well, bytes, remember, are really 8 bits. But if I'm dividing them up into groups of 4 bits and 4 bits, 4 bits is going to give me an 8 and a 4 and a 2 and a 1. Well, that's 15. That means I've got all the possibilities from 0 to 15 and all the possibilities from 0 to 15, which means a byte can be written as a 2-digit hexadecimal number. So let's talk about 91, because that is the number that we've been using throughout today's lesson. So if I was to take 91 and divide by 16, I know that 16 goes into 91 5 times, and that's because 5 times 16 is 80. And that's going to leave me a remainder of 11. And this is one of our troublesome numbers. So I go back to this table over here and I go, oh, 11, that's a B. So when I start thinking of my base 16 representation of 91, our base 10 value, this remainder is going to be a B. And now I need to take 5 and divide by 16. That's easy. It's just going to have a remainder of 5, and so that means that I have a 5 in my 16's place. Now, what's also helpful to remember is that 16 is really 2 to the 4th, and that means each of these digits represent 4 digits in base 2. So, of course, my 5 means that I'm going to have a 4 and a 1. I don't have any 2's. I don't have any 8's, because these are all powers of 2. And B, well, remember, B is 11. So I know 11 has an 8 and not a 4. That would be 12. And 8 plus 2 is 10. 10 plus 1 is 11. So I end up with 1, 0, 1, 1, 0, 1, 1. Base 2. My goodness, that does seem familiar. I feel like I've seen that number, oh, it was right here. And think back on this page as well. We saw that as well. Actually, the previous page. There it is right now, the 1011011. So the thing is, I can get to this number through any of the systems that we've talked about, through the octal system, or through the hexadecimal system, or through our usual base 10. What's nice, though, is that hexadecimal numbers are primarily used whenever we're talking about memory, whenever we're talking about bytes. But these octal numbers that we talked about are used a lot more when we're talking about something that's going to be human readable. Of course, humans are used to seeing 0 through 7 as digits. We aren't so used to seeing A through F as digits. So I want to kind of do a real quick recap at the end. Keep in mind that when I'm talking about my digits, when I'm talking about something that is decimal, decimal means that we're talking about base 10. So we're looking at 10 digits, and the digits are 0 through 9. If I'm talking about something that's binary, binary is base 2. So that means that we are going to have 2 digits. And our digits always start at 0. But here it's just, if I only have 2 digits, it's going to be 0 and 1. When I'm looking at octal, which is the third thing we talked about, octal means base 8. So that means that I'm going to have 8 digits, because there's 8 possible remainders from 0 to 7. And when I'm dealing with hexadecimal, hexadecimal is base 16, so I'm going to have 16 digits, and the 16 digits are 0 through F. Keep in mind, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Those are my 16 digits. If I want to convert something to binary, I'm going to divide by 2 and look at the remainders. If I want to convert something to octal, I'm going to divide by 8 and look at the remainders. And if I'm going to convert something to base 16, I'm going to divide by 16 and look at the remainders. And of course, this is assuming that I'm starting from decimal. One of the things that we notice is that if I wanted to convert between octal and binary, or between hexadecimal and binary, it was relatively simple. I want to convert each digit separately. So the thing is, if I want to convert from octal to binary, each digit, each octal digit, is 3 binary digits. So if I wanted to convert, 0 is really 0, 0, 0. 1 is really 0, 0, 1. 2 is 0, 1, 0, because that would be a 2 and no 1s. 3 has no 4s, a 2, and a 1. 4 is going to be 1, 0, 0. 5 is going to be 1, 0, 1. 6 is going to be 1, 1, 0. And 7 is going to be 1, 1, 1. And that's if I wanted to convert from octal to binary. If I want to do hexadecimal to binary, each hex digit is 4 binary digits. So I could think of zeros really being 0, 0, 0, 0. 1 is really 0, 0, 0, 1. In other words, I could put a 0 in front of all of these octal digits because none of these add up to 8. It's only when we actually reach 8 and say, well, that's an 8, no 4s, no 2s, no 1s. Or a 9 is really an 8, no 4s, no 2s, and a 1. An A, remember that's really 10, so that's really an 8, no 4s, a 2, no 1s. A B, that's really 11. That means I have an 8, no 4s, a 2, and a 1. C comes out to be 1, 1, 0, 0. D is going to be 1, 1, 0, 1. E is going to be 1, 1, 1, 0. And F is going to be 1, 1, 1, 1. So I have to convert each hexadecimal digit to binary, but I'm going to be converting them into groups of 4 binary digits. If it's octal, I need to convert it to binary because octal is 2 to the 3rd power. I'm going to convert each octal digit to the 3 binary digits, just the ones that I have in yellow. So these yellow digits. Now, what we're going to be doing over the next few weeks is we're going to be using this idea of transitioning back and forth from binary, decimal, hexadecimal, and octal number systems. We have to be fairly fluent in this translation because the computer will be giving us numbers in all of these different forms. It'll give it to us in decimal because that's what we're used to. It'll give it in binary because that's the easiest for the computer to do. It'll give it to us in hexadecimal because it's easiest for it to deal with memory. And it'll give it in octal because that's the best, the closest way that humans have to look at something that's binary in a familiar digit system. So we're going to be using this numerical conversion between these two bases throughout this course, but most specifically in the next upcoming 2 weeks. So once again, this is Mr. Potter. Thank you for watching. Have a great day.